Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying Indefinite Integrals lecture 2. In this lecture we'll be solving problems of substitution. Okay, so let's begin a lecture with this problem. So we have integral cos of ln x by x dx, right? Now you can see that we have this composite function over here. Now if you remember from the previous lecture, we talked about two key ideas, right? The first one was look at the argument of composite function. So we have ln x and we have to keep that as the substitution, that is t. Why? Because we have to reduce this composite function into a regular function, right? That's the first idea, right? Now if you differentiate this one, we'll be getting dx by x equals to dt. Now you can see that this is being clubbed over here, right? So that's a fair substitution. So we'll be taking ln x equals to t, and that would give us dx by x equals to dt, right? Now this would be reduced to, this is cos t and dx by x is dt only. So that has become a very simple standard integral, right? So that gives our answer. And now let's look at this one. So we have integral x cube dx divided by 1 plus x raised per 8. Now in this case, we don't have any composite function. We don't have, right? But our second choice was to look at what's been clubbed with dx. So over here, x cube is being clubbed with dx. And x cube is what? X cube is the derivative of some constant multiplied by x raised per 4, right? So let's say if we have k x raised per 4 equals to t, then we'll be getting k 4k x cube dx equals to dt, right? So this gives us an idea that we can take x raised power 4 equals to t. That would also make this as 1 plus t square, right? And that's also favorable. We always want 1 plus t square, 1 plus x square, or whatever in the denominator, right? To get the tan inverse standard integral, right? So that's why x raised power 4 equals to t seems to be the substitution that is perfect. Okay. Now, if we differentiate this one, we'll be getting 4x cube dx equals to dt, right? Now, x cube dx equals to dt by 4. Okay. Now, if you plug this over here, we'll be getting integral that becomes dt by 4. And this becomes 1 plus t square. Now, we have got our perfect standard integral, right? And now let's solve the example. And this one is a little more complicated as compared to previous examples. Okay. So we have integral ln of x plus under root 1 plus x square divided by under root 1 plus x square dx. Okay. Now in this example, we have multiple observations. So the first observation is this is the composite function under root 1 plus x square. This is also a composite function. And we have this clubbing as well. Okay. So we have these three observations. So let's go by the basics. Let's take this one, this composite function as t first, right? Because that would also give us this clubbing. That would take care of this clubbing as well, right? So let's take under root 1 plus x square equals to t. Okay. Now, if you differentiate this one, what you'll be getting? You'll be getting 1 upon 2 times under root 1 plus x square multiplied by 2x because of chain rule. Dx equals to dt, right? So this part has been taken care of. This 2 and 2 gets cancelled out. So we have got x dx upon under root 1 plus x square equals to dt, right? But this x is extra over here. And to write this x, we have to open up this square. So we'll be getting 1 plus x square equals to t square, right? So x square equals to t square minus 1, right? Also, we have this x over here. Now I can see that it's still very complicated, right? We can write x in terms of t over here. X would be under root t square minus 1. We'll be getting one more under root term over here, although we'll get rid of this part because of this, but we'll get this part x equals to t under root t square minus 1, and you have to write this as t, right? So it's still very complicated. I don't think that's a very good substitution, right? So let's think of some other alternative. Now for the second option, let's take this argument of the composite function as t, right? So that would give us x plus under root 1 plus x square equals to t, right? Now if we differentiate this one, we'll be getting 1 plus 1 upon 2 under root 1 plus x square multiplied by 2x dx equals to dt, right? So if you take the LCM over here, you'll be getting 2 times under root 1 plus x square plus 2x dx divided by 2 under root 1 plus x square equals to dt, right? So this two is getting cancelled out. So eventually what we are getting, x plus under root 1 plus x square divided by under root 1 plus x square dx equals to dt. Now you can see that this portion is getting clubbed over here, right? This portion is getting clubbed over here, but we're getting this as an extra, right? We're getting this as extra. So in case this was not there, this would have been the perfect substitution, right? So that gives me an idea. What if we take this entire ln term as t, right? Because if we differentiate this one, we'll automatically get 1 upon x plus under root 1 plus x square. And this would cancel out this term, right? Think again. If we take ln of x plus under root 1 plus x square as t, so if we differentiate it, we'll first get 1 upon x plus under root 1 plus x square multiplied by derivative of this one. That same thing, right? So this and this would get cancelled out, right? So let's do that. So we have ln of x plus under root 1 plus x square equals to t. So if we differentiate this one, we'll be getting 1 upon x plus under root 1 plus x square multiplied by differentiation of this one. That would be 1 plus under, sorry, 1 upon 2 under root 1 plus x square multiplied by 2x dx equals to dt, right? So this multiplied by this because of chain rule, right? Now this would give us 1 upon x plus under root 1 plus x square multiplied by this would be 2 under root 1 plus x square plus 2x divided by 2 times 1 plus x square under root, right? So this two gets cancelled out, and this also gets cancelled out. Dx equals to dt. So ultimately what we have got dx upon under root 1 plus x square equals to dt. So this was our perfect substitution, right? But we didn't get in the first time because this was a complicated function. It was not a very simple function. So we had to do hit and trial multiple times, and we got this particular substitution as perfect one. Okay. So until now, what you were doing, you were remembering the standard formulae which were derived using the basic definition of integration, that is reverse of differentiation, right? But now you'll be remembering these advanced standard formulae which are derived using substitution, right? So we have these four: integral tan x, cot x, sec x, and cosec x, right? So we can see that first, second are similar, third and fourth are similar. So we'll be deriving first one and third one. You have to derive second one and fourth one in the homework, right? So let's derive the first one. So we have integral tan x dx. Now, the first idea that should come to mind after looking at this integral tan x dx should be to convert this into sin and cos by sin x dx divided by cos x by, because we can take cos x as substitution over here, right? That would club this portion. Okay, so let's take cos x equals to t. So that would give us minus sin x dx equals to dt on differentiating, right? So let's plug that over here. We'll be getting minus dt upon t. So this is nothing but minus integral dt upon t. Okay, so this would give us minus ln mod t plus c. Why mod t? Because cos can take negative values, right? If we talk about definite integral over here, as of now we're just talking about indefinite, but just in case if we talk about definite integral over here, so in this case we have to take this modulus, right? Because cos can take negative values, right? Always remember. So whenever you write this kind of format, you have to take modulus, okay? Just in case that this does not take any negative value, okay? So we have got minus ln mod t plus c, okay? Now this can be written as ln modulus of 1 by t plus c. We have taken this minus sign over here as a power, and we have written 1 by t in the modulus, okay? Now 1 by t is nothing but sec x. So this would give us ln sec x plus c. Okay, so this is our first derivation for integral tan x. And now let's derive the third one, that is integral sec x dx. Now we know that sec x and tan x are actually highly related in terms of derivatives, right? We also know the integral of sec square x dx. We also know the integral of sec x tan x dx. Why? Because sec x tan x is the derivative of sec x. Sec square is the derivative of tan x, right? So based on the reverse differentiation formulae, we know this one and we know this one too, right? But we don't know this one, right? So we can utilize this one and this one to find out the derivative of this one. Let's see how. So let's do one thing over here. Let's multiply and divide with sec x plus tan x in this entire integral. Okay. So we'll be getting integral sec x multiplied by sec x plus tan x divided by sec x plus tan x, okay, dx. Now if you multiply this over here, we'll be getting sec square x plus we'll be getting sec x tan x, right? Dx divided by sec x plus tan x. Now if we take sec x plus tan x as t, if we take sec x plus tan x equals to t, and if you differentiate this one, we'll be getting sec x tan x plus sec square x dx equals to dt, right? You can see that this is the numerator only, right? So what we have done this substitution and we've got the perfect substitution, right? Now this would become dt upon t only, right? Now this is very simple. This is nothing but ln mod t plus c. Again mod t over here, right? Remember the concept. So what we have got ultimately, we have got ln mod t. Mod t was actually sec x plus tan x plus c. Okay. So this is the final result. I can see that over here we have got this version as well. We have got this version, but we have to look at this version as well, right? So how do we do that? So we have sec x plus tan x, right? So let's convert this into sine cos. Okay. So sec x is nothing but 1 upon cos x, and tan x is nothing but sin x upon cos x, right? Now this becomes 1 plus sin x upon cos x. Now 1 can be written as sin square x by 2 plus cos square x by 2, and sin x can be written as 2 sin x by 2 cos x by 2, right? Divided by cos x can be written as cos square x by 2 minus sin square x by 2. Simple entities, right? Now this actually becomes sin x by 2 plus cos x by 2 whole square, and this becomes cos x by 2 plus sin x by 2 multiplied by cos x by 2 minus sin x by 2, right? Now this and this power gets cancelled out. So ultimately what we have got? We have got sin x by 2 plus cos. So let's write this in the next page. So we have got sin x by 2 plus cos x by 2 divided by cos x by 2 minus sin x by 2. Okay. And now if you multiply 1 by root 2 in both numerator and denominator, what will be getting? We'll be getting 1 by root 2 sine of x by 2 plus 1 by root 2 cos of x by 2 divided by 1 by root 2 cos of x by 2 minus 1 by root 2 sine of x by 2, right? Now we know that this is nothing but sin a cos b plus cos a sin b. Why? Because 1 by root 2 is cos 45 and 1 by root 2 is also sin 45, right? So this becomes sin a cos b plus cos a sin b. That is nothing but sine of a plus b, right? Sine of x by 2 plus pi by 4. Now if we talk about this one is cos a cos b minus sin a sin b, because 1 by root 2 is cos 45 and 1 by root 2 is sin 45 as well, right? So this becomes cos a cos b minus sin a sin b. So that actually becomes cos of x by 2 plus pi by 4, right? Now this actually becomes tan of x by 2 plus pi by 4, right? So that's why our integral becomes ln of mod of tan of pi by 4 plus x by 2 plus c. Okay. And now let's solve this example. We have integral cos cube x under root sin x dx. I can see that this is the composite function over here and sin x is the argument of composite function, right? So let's take sin x equals to t square. Why t square? Because that would eliminate this under root as well, right? So if we differentiate this one, we'll be getting cos x dx equals to 2t dt, right? Now we can rewrite this integral as cos square x multiplied by under root sin x multiplied by cos x dx. What we have done, we have taken one cos from here and clubbed that with dx, right? So this actually becomes 1 minus sin square x, right? Multiplied by under root sin x multiplied by cos x dx. So 1 minus sin square x is nothing but 1 minus t raised power 4, right? And root sin x is nothing but t, and cos x dx is nothing but 2t dt. Now this has been converted into your standard integral. So we have got 2 times t square minus t raised power 6 dt. Very simple, right? And now let's solve this example. We have 1 upon x raised power 1 by 2 plus x raised power 1 by 3 dx. Now we can see that this is not at all a standard integral, right? This is not a standard integral. So we have to do some kind of substitution over here, right? So let's take x equals to t square first. Why? Because that would nullify this power 1 by 2. But in that case, what we'll be getting over here? We'll be getting t raised by 2 by 3. That is not a good expression. That is as complicated as this is one right now, right? So now let's take x equals to t raised by 3, t cube, right? But in that case, we'll be getting 3 by 2 over here. That is again not working. So let's take x equals to t raised by 6. Why? Because that would take care of this power and this power, right? So this would give us dx equals to 6t raised by 5 dt. So this integral would become dx, that is 6t raised by 5 dt upon, this is nothing but t cube and this is t square, right? Now what you can do? Now this can be written as 6 times integral t cube dt upon t plus 1. Why? Because we have cancelled out t square from both numerator and denominator, right? Now this can be written as 6 times t cube plus 1 minus 1 dt. We have added and subtracted 1 and let's see why. Now this would give us this t cube plus 1, that is nothing but a cube plus b cube format, right? And we can write this as 6 times t cube plus 1 dt divided by t plus 1 minus 6 times dt upon t plus 1. Now this has become the standard format. We have to calculate this one now. Now t cube plus 1 can be written as 6 times t plus 1 multiplied by t square plus 1 minus t. Right? Basically a square plus b square, sorry, a plus b, a square plus b square minus ab divided by t plus 1. Okay, dt. Now this and this gets cancelled out. Now this again becomes the standard integral. So this one is the standard one and this one is the standard one, right? So we have to do like this. And now let's solve this example and I'll keep this as homework because it's a little tricky. Once you understand the trick, it's very simple to solve, right? So let's keep that as homework. So today's lecture was till here only, and in the next lecture we'll be talking more about substitution. So let's meet in the next lecture. Thanks for watching.